Okay, so welcome to the monad and effect session of this afternoon. And we will be starting with one of the distinguished papers of the conference, an equational axiomatization of dynamic threads via algebraic effects. And Cristina is going to give the talk.
Thank you. So this talk is going to be about denotational semantics for a form of concurrency where new threads can be created dynamically. And the main ingredients that we use to make this work is that we use abstract names to talk about ideas of pools of threads. And we also treat fork as an algebraic effect. And so the main point of this work is that we give a true concurrency semantics to a core functional programming language. But we also give a complete equational axiomatization for our semantics. And to do this, we use strong monads and algebraic theories. Okay, so the main idea of the semantics is that a concurrent program denotes a partial order with labels, also known as a POPset. Here is an example program which it's probably hard to understand now, but the main point is that it forks a new thread, and then it performs some actions, row, sigma 1 and sigma 2. And its denotation is this POPset on the right, where the labels denote observable actions, and the partial order denotes dependencies between actions that we can observe. So here time is going from bottom to top. So that means that sigma 2 must happen before sigma 1. And then if two labels are not connected at all, that means they might happen concurrently. Okay, and then here are some more examples of POPsets that denote programs, and they are just to show you the kind of things that we can build. So we can also build a diamond shape or an N shape, and then this last one is a special kind of POPset with holes, which I'm going to explain later, which we need for our semantics. And of course, the POPsets are a very well-established model of true concurrency. But in our work, we go a step further because we also give a complete axiomatization to our POPset semantics. And we do this by using algebraic effects. Okay. So of course, there's a lot of related work on concurrency, which I can't put on a single slide. There's work in process algebra, in concurrent cleaning algebra. Other people have already used algebraic effects to model concurrency. There's been work on using separation logic to reason about effect handlers that implement concurrency, and we've seen some of that at POPL this year. But the key contribution of our work is that we give a true concurrency semantics to a functional programming language, and we do this through an equational axiomatization. Okay, so in the rest of the talk, first I'll explain what I mean by dynamic threads. Then I'll show you our algebraic theory, and then I'll describe the POPset semantics and the main theorem of the paper. Okay, so the language we're modeling has a base type of thread IDs, which actually they are IDs of threads, of pools of threads, because sometimes it's useful to refer to multiple threads at once. And then fork is the only operation that can introduce a new thread ID. And what fork does is it creates a new child thread and copies the parent continuation. And then because fork returns some type, then a thread can check if they are in the left branch, then they are the parent and they have the thread ID of the child. And if they're in the right branch, then they are the child. And then waiting on an ID A means waiting on all the threads in A to finish. And then stop ends the current thread, and it signals to all the threads that are waiting on it that this thread is now finished. And then act just performs action sigma immediately. And these are the actions that we observe. Okay. So maybe you can see that this looks like a very idealized version of forking and waiting from POSIX, and this provided some inspiration. But what we are modeling is a fine-grained call-by-value lambda calculus with these 4 effectful operations. And the operational semantics is based on pools of threads. But I'm not going to show you the whole operational semantics, but I want to show you just some examples. And the main idea is that the observable behavior of a program is captured by a POM set labeled by actions. So in the first program, it starts by forking a new thread. And then there are 2 cases, one for the parent and one for the child. So the parent will do action sigma 1, and the child will do action sigma 2. And there is no dependency between these 2 actions. So in the POM set representation, sigma 1 and sigma 2 are not connected. But then, because sigma 1 is happening on the main thread, the parent, then it's connected to this special label S, which just signifies the main thread. Okay. But then, if I change the program a little bit, so I add a wait on A before sigma 1, that now means that sigma 2 has to happen before sigma 1, and this is reflected in the POM set. Okay. Right, and then I said that fork will copy the continuation of the parent. So this is what this example shows. So let's say that in the continuation of fork, there is an action row. And the point is that this action will get copied in the child. So in the POM set, we can see there are 2 row actions. And so this is the example from the first slide. Right, and then in this last example, I wanted to show that stopping actually ends a thread and throws away the continuation. So if there was an action row after a stop, then row will just disappear, and it doesn't appear in the POM set at all. And so what I will do later in the talk is axiomatize these 4 operations, fork, wait, stop, and act, using 9 equations. Okay, so now I get to the part about the algebraic theory. But right before that, I'll explain the type of thread IDs in more detail. So I said that it's a type of IDs of pools of threads. And so to refer to multiple threads at once, this type has a semilattice structure, meaning I can write terms like A plus B, and this refers to the union of the thread pools A and B. And then the term 0 refers to the empty thread pool. Okay. So in order to give the algebraic theory in a concise way, it's easier to use algebraic operations. But so far we have been using generic effects to represent the effects like fork and wait. So I want to first explain the correspondence between algebraic operations and generic effects before I get to the algebraic theory. So given a generic effect op that has type A to B, the corresponding algebraic operation will take a value of type A and 1 continuation for each possible value of type B. So we can apply this correspondence to the fork operation, for example, and then we would get this fork on the right that has 2 continuations, the parent X and the child Y. And the most important thing is that fork binds a new ID A, which is referring to the child Y. So A is bound in X, And because of this, fork is, well, it goes beyond the usual framework of algebraic operations, but it's still part of a well-behaved notion of theory, which I won't explain in this talk because I don't have time. So you can ask me afterwards if you want. And so we can apply this correspondence from generic effect to algebraic operations to all the other operations that I showed you. So wait will wait on all the threads in U to finish, and then it will continue as X. Stop has no continuation because its return type was empty. And act performs action sigma and then continues as X. Okay. And so the point is that these algebraic operations are just a different syntax with which I can write the same examples that you've already seen. And the POM set representation will remain the same. So yeah, you don't need to understand the details of how to translate from this top one to this one, but I guess the idea is that the term still starts with fork, and then there's one part for the parent and one part for the child. But with this new syntax, I can state the algebraic theory on one slide, which I think is quite nice. Roughly, the equations are divided into 3 groups. So the first one says that, well, the first one is about how weighting interacts with the semi-lattice structure on IDs. Okay, it's okay if you can't read all the details. And then the second group roughly says that weighting on A and stopping is a unit for forking, but it's a bit more subtle because we have to be careful about thread IDs. And then the last group says that weighting and forking commute with each other, and that fork is commutative and associative. And then the last equation about act just says that doing sigma and continuing as X is the same as doing sigma on a child thread while the parent is waiting for that thread to finish. Okay. So now I can explain the POM set semantics in more detail, and then also the completeness theorem. So the main result of the paper is this completeness theorem, which says that the terms in the algebraic theory of threads that I showed you just now correspond exactly to labeled partial orders with holes. And this is an extension of POM sets that we defined for our particular case, and that I'm going to explain next. And so this theorem also implies that the equations of the algebraic theory are both sound and complete with respect to equality of these POM sets with holes. And because we have this correspondence to POM sets, we can reason graphically about the terms of the algebraic theory. Okay, and this theorem doesn't yet say anything about how the semantics connects to the operational semantics, but I will get to that near the end of the talk. Okay. So far we have seen some POM sets that model terms. These are 2 examples that I already showed you, but these terms were all closed. So how could we model a term where there was a free variable like here, so like in this term where X is a free variable and also A is a free thread ID. So in order to model such terms, we introduced this extension of POM sets with holes. And the point is that the holes and the dotted lines that appear in these pictures, they are extra structure on top of a usual POM set. There is a way to interpret each of the operations as a POM set. So stopping is represented just as the empty POM set, sorry, not empty, POM set with one element that has this special label for stop. Then a variable is represented as a whole, labeled by x. And then this x has a potential dependency to the ID b, which is given by this dotted line. And the point is that x might use b in the future. And then because x is happening on the main thread, then it has a connection to this stop label. Okay. Then waiting is also represented as a whole x, but now with an actual connection to the ID a, because x is waiting on a. Then act is performing action sigma before the whole x. And then forking has two holes, x and y, the parent and the child. And the parent has a potential dependency on the child y because it knows the thread ID of the child. And then again, the parent is the main thread, so it is connected to the stop label. And maybe the most important thing about these holes, x and y, is that we can substitute other POM sets into them. And that's when we start using the dotted lines. Okay. So now we can give the denotation of this term from the previous slide, which had a whole x. So yeah, that's represented as a whole here. Then x is waiting on a, so there is an actual dependency to the ID a. And x also knows about this ID b, which refers to row. So x has a potential dependency on the action row. Okay, and now that we have this graphical representation for terms, it becomes easier to understand what the equations in the algebraic theory mean. So here, I just copied the equation for associativity of fork. And in this graphical notation, it becomes easy to see that associativity just refers to different ways of plugging z into y and then y into x. So the two possible orders that we can do that in. Okay, I've already mentioned the completeness theorem, which said that equality in the algebraic theory agrees with equality of POM sets with holes. And because of this, POM sets with holes form a monad, which we then use to give a denotational semantics to language with forking, waiting, stopping, and act. And then we show that this denotational semantics matches the operational semantics from the first part of the talk, meaning that denotational equality implies contextual equivalence. And also we show that the converse is true, but only for programs of first order type. Okay, in summary, I showed you denotational semantics for concurrent programs that can fork new threads and wait on them. A key idea was to treat thread IDs very carefully. And the main theorems were the complete axiomatization of the POM-sets with whole semantics, which we then extend to a mini functional programming language. And then show that this denotational semantics is both adequate and fully abstract at first order with respect to the operational semantics. And so in the future, there's many possible directions we could go in. And for example, we could improve the semantics to allow children to send values to their parent. And we would do this by modifying the types of stop and wait. We could combine our semantics with shared state, or we could explore alternative semantics for fork and wait, such as waiting on all the descendants of a thread to finish, for example. Yeah, and that's all. Thank you.
Thank you for the talk. Any questions? Yeah, maybe behind.
I was wondering about the expressivity of the source language.
Could you wait for the microphone?
Yeah.
There.
Sorry, thanks for the talk. I was wondering about the expressivity of the source language with regard to the POM-sets you showed in the first slide. There is the famous N POM-set, and I was wondering whether that's something that's definable in your language.
The N POM-set, yeah, it is definable. Yes.
How? Then I'm very curious to see how you do it.
Yeah, because, okay, I guess this is at the beginning. Okay, the idea would be that I can write a term where each action is a child thread. And then if I do that, if I spawn these threads in the right order, they can wait for each other.
Okay, so you can define any POM-set then?
Yeah.
Okay, thanks.
I think it's working.
Really? Okay, yeah, okay. Okay, in the case of the state monad, which is much simpler, yes, the correspondence between the monad and the equational theory can be expressed as a normal form theorem.
Yes.
Yes. And so I was wondering whether the theorem, like the main theorem that you give,
Yeah.
is expressed as a normal form theorem and some kind of rewriting theory, and how you do that, yes.
Yeah, that's exactly how we proved that theorem.
Okay.
Yes, by finding normal forms for the equational.
Okay. So it's purely
theory.
equation. Yeah, yeah. So
Yes.
it's too good. I mean, it's really brilliant.
And
yes.
yeah.
Okay, any more questions? Yeah, so maybe the next speaker could already set up.
I asked a technical question in the chat, but I have a simple beginner question. The associativity examples, intuitively we expect the three threads to be independent of each other, but the POM-set you have in the middle looks like there is some sequential order. So what did I miss?
Okay, so right, so there, because X in that example knew the thread ID of Y, then there might be a dependency from X to Y once we substitute in another POM-set for X, and that's what the dotted line was meant to represent.